Okay, so today we are going to see a basic problem of bit manipulation. So we are given two numbers, 10 and 20, and the binary representation of these two numbers are 0, 1, 0, 1, 0, and for 20 is 1, 0, 1, 0, 0. You can see we just need to return the bits, those are different. Return the count of those bits. So here there is a 0 and 1, so count is 1. And again there are two different bits, and again we have two different bits, so total we have four different bits, and so that is the reason we return 4. So now let us see the explanation or the ways we can solve this problem. So first let us look at the naive approaches that we have, and then later on we'll see the optimal approaches to solve this problem. So the first approach we have is we can run a for loop till let's say we are dealing with 32-bit integers over here. So let's say there are 0, 0, 0, and there are like 27 zeros, and then we have 0, 1, 0, 1, 0, 10. So this is the binary representation of 10 in 32 bits. So we loop till 32, and then we check each occurrence of bit and then increment the count and then return the final count value. So this is how it runs. First it checks this bit. This is called the LSB. Okay, so it checks this bit and then it goes on to the next bit, and then we encountered a 1 and we have 1 in the count. It checks this bit and then again it goes on to the next bit. We get a 1, we increment the count becomes 2, and then it goes on over here, and then again it goes on to the rest of the 27 bits. You see, this is not an optimal solution, because even after the number of ones are over, we still iterate through the rest of the 27 or 28 bits over here. So ideally the program should stop over here, and that would be an optimal solution. This runs in theta of n complexity, and space is of course big O of 1. The other approach that we have is using strings. So in strings the problem is same. We again use for loop over here, but we just convert this into 2-bit integer so that we can easily iterate through the number of bits using a string. Again it takes theta of n and space as big O of 1. Now let us look at an optimal approach of solving this problem. We can solve this problem using bit manipulation. Now I'll tell you about the algorithm that we are going to learn today, and first I'll discuss the approach that we are going to follow, and I'll tell you the operator that we are going to use in this problem. So let us first write the inputs again. So A is 0, 1, 0, 1, 0, and B is 1, 0, 1, 0, 0. Okay, so this is 10, this is 20. So whenever we see difference or we need to find the number of bits those are different, in this case we always use the XOR operator. The XOR operator, and this is what we are going to use here. We see the bits are different, so this is where we use the XOR operator. Let us see the logic gate table of this operator. 0, 1 we get a 1, 1, 0 we get a 1, 0, 0 we get 0, and for 1 and 1 we always get 0. So we see that whenever there is a difference in the bits, we get 1, difference in bits, and we get a 1. So this is the operator we are going to use this. So what we are going to do is initially we compute int result. Result will have the XOR operation of these two numbers, and then what we're going to do next is we are going to do apply the algorithm that we are going to learn today, and that is called the Kernigham algorithm. So using this algorithm, we are going to solve the problem. Now let us see how the Kernigham algorithm works. So the Kernigham algorithm says that in 32-bit integers, or let's say, or even 64 bits, it works on either of them, both of them actually. So 0 0 0 0 0, so again we have like 27 zeros. We are taking 10 again, so 0 1 0 1 0. So Kernigham algorithm does not iterate on every single bit and then return the count. It directly checks for wherever we have 1. Okay, here we have 1, and then it checks for the next one, and again it jumps over here, and then it jumps on the next one. So that is how it works. So this is a very fast algorithm, and takes log n of time, which is quite fast. And let us see the working of this algorithm. I'll write the pseudocode of how it works. So we run this in a while loop till we get a 0, till we get all the numbers as 0. So while result is not equal to 0, and like I said, result is having the XOR operation of these two numbers, 10 and 20. Not this, yeah, 10 and 20. So again, now this is what we are going to do now. So result is equal to result and result minus 1. This is what the Kernigham algorithm says, and whenever we get this, we increment the count and return the count. That is the answer we're going to have. So now I'll show you the working of Kernigham algorithm. Then it'll be better for you to understand the working of it. So in the first iteration, what we are having, so as we saw on doing the XOR operation, result is having 1 1 1 1 0. This is actually 30. We got this on doing 10 XOR 20. So this is the result we are having according to the algorithm, the Kernigham algorithm. So result is equal to result and result minus 1 is what we have to do. We are already having a result, so the next thing we have to do is minus 1. 30 minus 1 is 29. So what we do is 1 1 1 1 0. Binary representation of 29 is 1 1 1 0 and 1. Yes. Okay, so according to the algorithm, what we do is we do an AND operation. For AND operation 0 1, we always get a 0. 1 0, we get a 0. 1 1 and 1. So the number we got over here is 28. This is the first iteration. Let's go on the next iteration. First iteration and the second one. What happens is we do 28 minus 1, we get 27. So we do an operation between these two numbers. So the binary representation of 28 is 1 1 1 0 0 0, and for 27 is 1 1 0 1 0. On doing the AND operation, we get 0 0 0 1 and 1. What we are getting is getting 24. Yes, 24. So again we do minus 1, and then we get 23 binary representation of, and then we do AND operation on these two numbers. Let us see how it works. 24 is 1 1 0 0 0, and 23 is 1 0 1 1 and 1. We do AND operation on these two numbers. 1 0 is 0, 1 0 is again 0, 1 0 is 0, 1 0 is 0, 1 1 is 1. So we got this is 16. 16 minus 1 is 15. So let us see how we do with this. Okay, so 1 0 0 0 0, 15 is 0 and rest of the bits 1. Okay, and operation 0 1 is 0, 0 1 is 0, 0 1 is 0, 0 1 is 0, 1 0 is 0. So we see that this is how the algorithm works. This is not a dry run of the program, but this is I just wanted to show you how the algorithm works. I just want you to notice a pattern over here. So initially we were having 20, we had 30 in the result, and we see that 30 was this was 30 and this was 29, this was 30 and this was 29. So we see that after every iteration, the LSB, the leftmost bit, the leftmost set bit is turning off. You see, after this we get a 0, and this is when we increment the count as 1. Again you see over here LSB is 1, and after the result, after the AND operation, we get a 0 here, and again we increment the 1 count becomes 2. Again we see over here the LSB is 1. After doing the AND operation, it becomes 0, so the count is now 3. VC1 is over here, this is the LSB, and on the AND operation we see that we get a 0, and this is when the while loop ends, and this is the final time we are going to increment the count. So this is how the Kernigham algorithm works. It works in log n time and takes big of 1 space quite fast, but this is what the interviewer would be expecting from you. But there is another approach which takes constant time. It takes theta of 1 time and space as usual 1. So this is the most accurate, as in the most fast solution that we have for this problem, and this is what the interviewer would be expecting, and this is where it gets a bit tricky. So this we'll see in the next video. Now let's see the execution of the problem. Okay, so first we initialize count is equal to 0, and now let's compute the XOR of these two numbers, A XOR B. Now let's run a while loop. While we get a 0, what we do is result is equal to result and result minus 1, and whenever we get this, we increment the count and return count. So this is a simple problem. Let's compute and run. Okay, we see we get a 4, and expected output is also 4. Let's submit the problem. Okay, yeah, so the answer is correct. It passed all the test cases, and the algorithm also runs in log n time. As I said, there is another approach called the table lookup method. This is the method that we are going to see in the next video, where we can see the most optimal solution of this problem and solving that in theta of 1. Thank you. Okay.